No, officially. So if you're having trouble getting the book, let me know. It's not a ton of stuff I could do for you, but I could try to do a little bit more. Get into that chapter 1 homework as soon as you can, so you have questions about it. Yeah, let me make this official. We are going to have a quiz on, I think I said this last time, basically. We're going to have a quiz on chapter 1 on Monday. Right, so yeah, it's due Sunday night. We'll have a quiz on Monday. I'm always here at 8 a.m. before class starts. So you can come ask questions or whatever. Okay. If there's no questions, we're just gonna get right into chapter 2, to be honest, if there's no questions from chapter 1. I had some people ask a few questions in office hours, but if everybody else is doing great, that's awesome. Okay, so what I want to do, we're going to officially step into real calculus today, but we're going to get there on the heels, like on the shoulders of stuff you've done before. So let me ask this. Does anyone remember horizontal asymptotes of rational functions? Does anyone remember how to find it? So let me give you an example. Yes, Chloe says yes, she does. I'm going to actually use a physical whiteboard. I'm so excited. Just knock everything over. Bum, 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 bum. Bum, 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 bum. All right. You guys see me all right? I think so. Okay. Oh, let me do this before I forget. Boom, 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 boom. Ow! There we go. Okay. So for example, if I had this, oh, Jeff, did you do something crazy? You probably did. There. Okay, I don't want to do something crazy. All right. So somebody help me out. Does anyone remember how to get the horizontal asymptote for this?
Don't you factor the bottom and then do like that?
Will the bottom factor? No, right? The only factors are 3 or 3 and 1. Everything's positive, so 3 and 1 makes 4, not 2. So you can't factor the bottom. Right, so I'm not talking about simplifying it. I want to know what the horizontal asymptote is. I think you're thinking about vertical asymptote. We'll talk about that in a minute. I'm talking about horizontal.
Don't you look at the powers of like the numerator?
Good.
Denominator?
So tell me this. This is exactly right. Which one grows faster, the top or the bottom?
The bottom.
The bottom. Does everybody agree? The bottom definitely grows faster because it's got a squared term. So let's do this. Let's do this. Okay. Somebody help me out. I'm going to show you a little bit later a shortcut in the calculator to make tables that some of you guys probably know, but I want to make sure everybody knows. So what you just said is the top degree is smaller than the bottom degree. And the reason that's important is because that means the bottom will grow faster the bigger x gets. Now, think about this. Before I make this table, what should happen if I am dividing by something that's growing faster than the top is? What should the answers get closer and closer to?
Zero.
Zero, of course. Because if I'm dividing by bigger, 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 my answer should get smaller, smaller, smaller. And it should eventually get to go to 0. So let's try this out. Can you guys, let's see who can do this for me. If I put a 1 in, obviously, what do I get? I get 0. That's yay. It's pretty cool with that. I get a 0. Okay. All right. What happens if I put a 10 in? Can somebody help me out? I'll get 9 over 123. Is that cool? Do you guys see that? 9 over 123. Can somebody tell me what that is roughly? It's like 0.0831. I don't know, I'm just making shit up.
0.073.
Oh, okay. I was close. Now, what if I put 100 in? What's the top?
99.
99. And what's the bottom? Oh shit. 100 squared would be 100. So it'd be 10,203. Is that cool? Is everybody with me? What's happening? So does anybody not understand why I'm making this table and why I'm doing this pattern here with the X's? Is everybody cool with what's happening? Okay, because the idea behind a horizontal asymptote is what happens to the function when X gets really big, positive or negative. So somebody help me out. What's that?
0.0097.
0097. Right. So this is so it started off at 0 because that's the x-intercept, but then it got here and then it's going down again. And if I do 1,000, it's going to get even smaller. So let's see what that's going to be. 999. 1,000 squared is 1,000 thousand. So it's 1,000,000. So it'll be 1,000,000 2,000 and 3. Do I have enough stuff in there? No, there we go. 1,000,000 2,003. And when you divide that, you're going to get 0.00 something more than likely, or maybe. You guys, everybody okay out there? Do you guys agree with me that this is enough evidence to say that these are going to 0? Okay. And some of you guys remember that shortcut, yes? Whoever said that in the first place, when the top degree is smaller than the bottom, I'm going to have a horizontal asymptote at y equals 0. Okay, so some of you, your pre-calculus teachers, might have used the actual notation for this, which is has anyone ever seen this notation before? Few of you guys. So the way this is read is the limit as x approaches infinity. And really the real way to say that, because infinity is not a location. Everybody with me? I always love it when somebody has to graph an answer and they put infinity on there. Right? This is not good. Never do this, because then what the hell is this? What's that? If that's infinity, what's over there? Yes. Okay. Yeah. So the limit as x gets big, gets large, of the function is 0. Meaning, as you let the inputs get big, unbounded, just let them get big, the outputs will get smaller and smaller and approach 0. Let me stop for a minute. So this is just the formal notation to capture what we said over here. Yes. Maybe. Okay. So let me do one more example with a vertical asymptote real quick. Maybe I'll finish out horizontal just to remind you guys, because this is going to come up this semester. I'm going to erase all this. Everybody ready? Okay. So horizontal asymptotes. One thing is, if the top degree is smaller than the bottom, you got a horizontal asymptote at 0, right? Meaning the graph might look something like this, right? That's one example. Is everybody with me? So that's an asymptote at 0. If the degrees are the same, top and bottom, what happens? All right, so anybody remember this? If the degrees are the same, what's going to happen?
Isn't it like it's like a ratio of the numerator and the denominator?
Yes, the ratio of what? And
Or like the
Chloe, you're
first
one
time.
step ahead of me, Chloe. Go ahead, sorry.
It's like it will be like 2/4.
Yes. Okay.
Yeah.
Okay. All right. Let's see how patient you guys can be. Here we go. Real quick. Real quick. And you guys are all like, dude, it's all I am here is patient. All right. All right. I got you. Real quick. Real quick. If I make a table again. So what we got here is the limit as x goes to infinity of this. The claim is it'll be 2/4. Of course, otherwise known as 0.5. Now, real quick, just go with me. Anybody have the calculator ready? You can help me out. See, that's my calculator. So let me let x get really big. So when x is 10, this will be 203 over, Jeff, what the hell, 400, 331, is that true? I think it's true. You guys can double check me, maybe?
Yep.
And that's roughly, I'll say 0.64. You know, what is that? That's a guess.
0.613.
0.613?
Yeah.
That's not, all right, that's not bad. If x is 100, so I'm letting x get really big, and then I'm investigating what's happening. If x is 100, oh geez, all right, what's that going to be, Jeff? 100, so it'll be 200, 100 plus 3 over 400,000 minus 700. Oh, Jiminy Jeebus, Jeff. 301. I think that's what it is. And this is already like, I would say 0.51. I don't know. Double check me on that. I'm just guessing. Hopefully I did that right. That would be great if I did. I think I did. Okay.
0.050.
0 point, sorry?
0.050.
050?
Yeah, so it's 0.050.
No. It shouldn't be that. Let me see. Did I already do something wrong? 100. That's right. So 1, 2, 3, 4. 1, 2, 3, 4. Yeah, that's true. What did I did something wrong. Okay. Let me do this. I'm just trying to speed through that. I'm going to show you real quick right now how to make the calculator construct this for us, right? So let me pull this dude up. Where are you? Oh, I didn't have it open. Darn it. There it is. So you guys, on the survey that most of you have done, I think most of you said you've used this TI calculator at least a little bit. So real quick, this is kind of nice. Let's put in here, so the y equals, let's put in here this function that I'm using right now. So it'll be parentheses 2x squared plus 3 divided by parentheses 4x squared is 7x plus 1. Okay, I like it. Is everybody with me? Let's make this calculator do some work. Cost enough money, right? Above graph, you can see where it says table. We're going to go there in a minute, but let's first go here. Table set. Let's set this table up. So hit second window. And I've already got it set up in a special way, right? So you guys are probably used to this kind of setup. Let's make this 0. You guys are probably used to seeing the table like this, right? Now, some of you guys probably know this, but this is kick-ass. If you change this one right here, the independent variable, meaning the input, right? Independent variable is x, the input. If you change that to ask, then that means exactly what you think it might mean. It's going to ask you what you want to use. So I can then put in there, what did I use? 10. Bam. Here's what this should be. I don't know what I did wrong up there. It should be this. 0.51. I was close to what I thought. And 1,000. Bam. And then 10,000. Bam. All right. Do you guys, what is the important part of what I'm doing right now? Can somebody tell me what the important part is of what I'm doing right now? What are we seeing from this table?
It's getting closer to 1/2.
Yes, which is what the prediction was, right? I like it. So this is the way. Can we plug infinity in? Hell no. Hell no. So in some sense, I can hold 10, right? Couldn't I hold 10 things? Can't I? I can sort of, there's a way that I can think of I'm holding 10, right? There's no way to think of I'm holding infinity or I get to infinity. I can wait 10 seconds. I could do that. I could wait 10,000 seconds. I could do that. I can't wait infinity seconds and then go, okay, I'm done waiting. No, right? Because infinity is a process. It's not a location. Okay, maybe. So what I'm trying to say is, let me stop sharing because this is not important. When you're trying to analyze a function, either at a point that you can't get to, or at a point where things go haywire, we'll look at that example in a minute. A table is a way to get a pattern so you can predict what it wants to do at that weird place. So one weird place is obviously weird. Infinity, right? Infinity is a weird place because it isn't a place. It's not a location. So you can't even plug that in because it's not even a value. Okay, I like it. You guys doing okay out there? Okay. Now, what about vertical asymptotes? Let me get back up here. Go away again, chair. Vertical asymptotes. So for example, let's start off really nice. Yeah, I like it. What's the idea? Well, first off, can anybody just tell me what the vertical asymptote is for this guy?
3.
3.
Yes, and more specifically, x equals 3, right? Because the vertical asymptote is a line, so it has to have an equation of a line. So in this case, and that's because vertical asymptotes come from the domain. Vertical asymptotes come from issues in the domain. We set up a wall and we say you can't go here. It's a trap. Pull up, right? Okay. No Star Wars people? Okay, that's fine. So here, the vertical asymptote, we get it from the domain. What's not allowed to happen? The bottom can't be 0. So x can't be 3. So then at 3, vertical asymptote. I like it. So what, but I can still ask this question. What happens at 3? And why? Right? Am I allowed to plug 3 in? No. But something still happens at 3, correct? Or better said, something still happens around 3. So we can do just like we did earlier. We can make a table of values. Now the trouble spot is 3. There it is, 3. The trouble spot is 3. So when the trouble spot was infinity, I just made the inputs get bigger. The trouble spot is 3. So what can I do with my inputs to investigate what
Approach
happens?
3.
Say again?
Approach 3.
Yes, good. I like it. And I often, has anybody ever seen, there's a movie called The Blob? There's a point to this. I love you guys so much. You're all like, what the hell is this guy on? Okay. And I'm talking specifically about the 1980s Blob, but you can talk about the one from the 40s or whatever. So at the beginning of the movie, this thing crashes, is a little bubble stuff, little gelatinous thing, and it's moving around. And this guy comes up and he's like, that's a weird thing. In that spot right there, weird shit is happening. Now, the mistake he made was he actually touched the weird thing. And then it gets on his hand and eats him and all kind of stuff, right? Now, all right, sorry. Right? The prerequisite to this course is not certain movies to be watched. Okay, so you're fine. So the point is, if something weird is happening at a point, and we're humans, we're curious, we don't want to get to that point because then weird shit happens. We want to get close to it and go, oh, and then we want to back away, right? So how does that look in a table? Well, I can say, all right. So there's an idea of approaching it from the right and from the left, correct? I have this weird thing. I can approach it from this side and I can approach it from this side. So what if I put 4 in? What do I get when I put a 4 in?
2.
2. I like it. 2 over 4 minus 3, so I get 2. What if I put a 3.5 in? And again, if you want to, you can use your calculator, you can make the table, or you can just plug a 3.5 in.
4.
4. I love it. Please let me know if you're not sure where something's coming from or something, right, everybody? What if I put a 3.1 in?
20.
20. 3.01.
200.
200. And you can already guess what's going to happen. Now, let me come at it from the other side. What if I did, what do you got, Jeff? 2. Put a 2 in. What do you get?
-2.
Yeah, -2. What if I put, where am I going? Oh yeah, 2.5. So I'm trying to get close to 3, right? So what if I put a 2.5 in?
-4.
Okay. Say again, sorry?
-4.
-4? Yeah, okay. Jeff, I'm having a great moment here. 2.9, that should be where it's -20, right?
Yeah.
It'll kind of mirror this. And then 2.99 would be -200. You can verify.
Yeah, it is.
Not calling you crazy. So it does pretty much what we know it should do. If you remember this kind of stuff from pre-calculus, it goes, what's the limit as x? Let me see if you guys can kind of naturally get what I'm going to write. What are we kind of getting close to again? What value? What value are we investigating?
3.
3. So this side is going to 3 from the right, from the positive direction. Is that, you guys see what that means? So I'm going to capture this information right there. As I approach 3 from the right, from the positive direction, what does my outputs, what do they do? What do my outputs do?
The values are increasing greatly, so would it be positive infinity?
Good. Yeah, and actually, I love what you just said. In a lot of these problems, you might want to go ahead and make a plus sign just to make it really clear. Do you mean positive infinity? Because sometimes little stray marks make it look wrong, and then I might count it wrong. What about the limit? So let me, before I even write this, don't say anything. Can you write a similar statement for this? Don't say anything. Just write it. Can you write a similar statement for what we did here? Okay, who's got that?
The limit as x approaches 3 from the left side of f of x equals negative
Yeah.
infinity.
And what did you put here for that?
Minus sign.
Good, a little minus sign. Of the function is negative infinity. So as I approach it seems that these are going, in fact, I've got some more information here. 2 is -2. And so it's going, yeah! And then on the other side, 4 is 2. And then it's going, wah! Okay. Something we should all be very familiar with. Yes, is that cool? And just as a little bonus thing, what's the horizontal asymptote? What's the limit as x goes to infinity? What situation am I in?
Y equals 0.
Yes, good, because the bottom degree is higher than the top. What is the degree of the top? What's the degree of the top right now?
0.
Good, because degree means the number of variables that you see. So how many x's do I see up here? None. How many do I? 1, right? So it's really the power, but then that confuses people here. So it's really the number of x's you see. So the limit of this will be 0. So that means y equals 0 would be the horizontal asymptote. I like it. Okay. So some of you guys, this is all fantastic. You understood all of it. Some of you guys forgot some of this stuff. And does this notation make kind of natural sense? We had to pick a way to denote these two kind of things. So this kind of made sense. Hopefully. Okay. All right. Now, there was something else I was going to do. Shoot. What was it, Jeff? Oh, that's right. Let me do, so just so you know, I'm not really going through chapter 2 chronologically. So I'm sorry ahead of time. We're going to do one more example, and then I'm going to kind of go back and start marching through the sections. I just needed to lay a lot of groundwork out, okay? So if you ask me what section we're in right now, I'm not really sure. Let's do one more example that's really freakadelic. Can somebody, what do you think you should try to do first when you have a limit question? Like, for example, real quick side example. Why is this an easy question? Why is that one, I don't even have to do much work at all? Why is that one an easy question? Is there a problem at 1? Does that function have an issue at 1? Does it have an issue? Sorry? Go ahead.
No, there's no issue at
There's
1.
no issue. There's no issue at 1. The input isn't infinite, and the input doesn't make anything undefined or anything. Are you guys with me? In fact, what is this limit then? Why is this one easier? Do I have to make a table of values and step close to 1, or can I just plug 1 in?
You can just plug 1 in.
Yeah, what do you get?
2.
2. Yeah, crazy. All right. So, can somebody identify why this one is not that simple?
There's a
Because-
0 in the denominator.
Good.
It's undefined.
It's worse than that. So the 0 in the bottom makes you feel like the answer is going to be some kind of infinity, correct? Is that cool? If the bottom is 0, then it's going to be either positive infinity or negative infinity. Yes? Maybe? Okay. But what's the numerator at 0?
0.
Good. So think about this. Anything divided by 0 is some kind of infinity. Yes? That's not quite true, but we're going to show why. 0 divided by anything is what?
0.
Yes. So you have 0 divided by something, so the answer should be 0, but you have something divided by 0, so the answer should be some kind of infinity. What the shit? Yes? You guys understand the problem here? Getting something like 1 over 0 kicks ass. Yay. Because that means it's just some kind of infinity. Okay, I just got to figure out if it's positive or negative. Getting 0 over 0 is worse because it's going to take some work. It's not going to be quite as easy. So this isn't undefined. This is called indeterminate, which basically is just saying it's freaking worse than undefined. Is everybody roughly with me? The answer to something that's indeterminate can be negative infinity, it could be infinity, or it could be anything in between. Okay. And just as a quick, no, okay, we're not gonna do it. Let's do this. So anybody have an idea of how to investigate this? You should. How do I investigate?
Plug in values that are close to 0.
Yes, kick ass. Okay, so listen, you guys are gonna help me out. You guys all have your calculators ready. Give me a number to plug in. Like approaching 0 from the right. So maybe like, let's just start at 1, and then we'll step in by factors of 10. Does that sound, you guys with me? So do you see the idea? So you guys got to help me out. What do I get when I put a 1 in here?
0.84.
84 business, who cares? And then somebody else help me out. What do I get when I put a 0.1 in here? Oh, let me double check. You got to be, okay, this is a really beautiful place to talk about trig. Did anybody get a different answer?
Yeah, I did. I got a 0.0175.
All right, let me see. Oh, I've got the thing up here, Jeff. Here. So the really terrible thing. Can anybody tell me what units angles have? Oh, somebody's got to chat to me.
Degrees.
Oh, Carmen's got the idea. Yeah, angles can have degrees or
Radians.
radians. Does anyone realize there's an answer to this question? Which unit is generally better?
Radians.
Yes. Does anyone know why the answer to that question is radians?
Because pi?
I appreciate that. That's an awesome guess. Does anyone remember what a radian measures? Don't say angle length, because that's not actually directly correct. Does anyone remember? So here's a circle. It's got a radius of r. Does anyone remember what radian actually directly means?
Supposed
Okay,
to.
what? Go ahead.
Oh, isn't it supposed to like represent its point on a graph?
True. So here's the cool thing. You guys ready? What if I took this radius, put it here, and then I bent it, right? I bend that radius and I put it here. So I took this, not that far, Jeff. That's all right, Jeff. It'll be fine. So I take the radius and I bend it and I put it on the circle. So one radian is how far I would make it on the circle if I walked a radius around the circle. Doesn't it make sense we called it freaking radian since it's based on the radius? Isn't that kick-ass? What if I had a bigger circle, Jeff? Your whole thing goes to shit. No, it doesn't, because now it's longer. If I bend it and walk, I stop at the exact same, well, shit, it's a little bendy. So you see the amount that this opens is the same no matter how big or small the circle is. So why are radians better than degrees? Does anyone know where 360 came from? Is it like, did it have to be 360 degrees? Have you ever thought about this? Why is it 360? Did it have to be 360 degrees? You're all like, dude, stop it, man. All right. No, it didn't. It could have been 4,293. It could have been 7. It's completely made up. So why did we use 360? Where else does 360 show up? Where else does 360 show up? Man. No? What about time, roughly? Right? 60 seconds is kind of some 60s. 360 is very easily divisible, isn't it? Doesn't 360 have a ton of factors? In fact, it's roughly, there are some better ones, but 360 is a really good one with a ton of factors. So that's why it was just arbitrarily chosen. We just arbitrarily chose to break this up into 360 little parts. I really want you to understand. We just had to make a choice. But radians are actual lengths. They're not some arbitrary choice. They're actual lengths based on the parameters of the circle itself. That's why radians are better. They're physical. Degrees are not. Degrees are made up shit. Right? That doesn't mean degrees are useless. It just means radians are better. Okay, now, with all that stuff said, is everybody all right? Have I said too many things? Are you guys okay out there? With all that stuff said, you got to be really careful what mode your calculator is in. Basically, the shortcut is anytime you have a variable part that's not inside of a trig function, you have to use radians. So why not just always use radians or mostly use radians, right? Okay, so what mode am I in currently? Let me hit the mode button, and I am currently in radians. Yay! Sorry, I didn't mean to yell. So if I do sine of 1 divided by 1, I get 0.84. Good. So everybody should get 0.84. I like it, right? What about 0.1? What do you get?
0.998.
0.998. Sweet. And now what about 0.01?
0.99998.
Yeah, dude.
Approaching 1.
It gets really crazy. Wait, am I sharing my screen still, Jeff? Yes, you are. Let me stop sharing so you guys can see 0.999 is crazy. So it pretty quickly shows its cards. And again, if I go from the other side, if I start at, where am I at? -1, and then -0.1 and -0.01. Let's see, you shouldn't have to do any work. It's going to be all the same stuff. I should have went the other way, sorry. I kind of like to do it this way. The book does it in different ways. I kind of like to go like this. So visually it makes more sense. You'll actually get 0.84, 0.998, 0.99998. So what is this limit? What's our guess? And this is still just a guess, but it's a pretty good guess. What's the guess?
1.
1. Wow. It looks like it's going to 1. Could the answer be 0.999999999999972? Yes. So this is not good enough to be exactly right, but it's good enough to give a reasonable guess. Okay, maybe. Maybe. So this is the best tool we have when we first start looking at limits at weird locations. Making a table to kind of feel it out a little bit, to kind of get really close to the weird alien thing, but don't touch it, right? So why are limits so powerful? Because they allow you to investigate something close to a problem. No, you weren't a problem. Close to a problem spot without actually getting to the problem spot. Okay. Now, so that is the idea of limit. And real quick. Let me write this. So what's the limit as x goes to 0 from the right? It was 1. What's the limit as x goes to 0 from the left? It was also 1. Therefore, I could just say the limit is 1. Let me see if you guys are cool with that. Since the limit from the left and the right agree, the function has 1 limit at that number. Now, I don't know if anybody's tried this. If I were you in this class, the first step in a lot of problems would be to graph the thing I'm looking at. That's not good enough work for most things. But did anybody try to graph this? Let's see what I get. Let me do zoom 6. There you go. So what happens, I mean, if you trace it, tracing is not the best thing in the world. Look what happens right here. What happened right there? What's weird right there? Anybody see something weird right there?
The Y value disappeared.
Yes, and what do you think that's telling you?
That it like errored or that it's indeterminate.
Indeterminate, or the calculator, all it
Undefined.
knows is it's undefined there. But yeah, we know better because the form of it. But the calculator's like, I don't know what it's defined to be here. But if you can kind of see right here, you can see it going from above and going from below. It kind of mimics what we did in the table, right? I like it, but there is like an open circle there because I'm not allowed to put a 0 in. There's still an open circle there. Okay, I like it. I like it a lot. Okay, now. I'm gonna erase all this. So that is a few fundamental things about limit by itself. So I'm doing things a little bit out of order from the book because I don't like the way the book does things. Limits exist by themselves, correct? That they're just an idea. I can use it anytime I have a weird thing and I want to investigate. I can use the idea of a limit. Now I want to discuss something that limits can help us investigate. So for example, let me see. I had an idea. That's right. I love it. Okay. Okay, this is going to sound very disconnected, but too bad. If I had a position versus time. So let's say somebody starts moving, somebody's right next to me, and then they start moving away. So here's their position versus time. Spot. So that's the graph, and this is a pathetic graph. This is a disgusting graph if your answer is a graph. What am I doing with this right now? Discussing an idea. So I don't need scale and all that kind of stuff. You guys get the idea. This person is walking away from me. Can anybody tell me anything about the speed at which they're moving?
It's constant.
Good. I love it. So some people out there are like 7 miles an hour. No, so I don't know a scale, so I can't give any specific numbers, but I do know that the speed, the velocity is constant. What about the graph told you that?
It's just linear. It's nothing of this velocity is changing.
Yeah, it's not curving. The amount of distance they get away from me is constant over time. Therefore, and that's the velocity. Is the velocity on this picture somewhere, somehow? Because this would tell me the position, maybe 1, 2, 3 meters, 1, 2, 3 seconds. So 3 seconds later, they're 2 meters away from me. You guys okay? Does that make sense?
Yeah.
Just to give this a little more detail, is the velocity present on this graph somehow?
Yes.
Yes. How?
It's the line is indicating the
How?
velocity.
What about the line is indicating?
That it's a constant speed.
What about the line?
It's slope.
Slope, kick ass. All right. So velocity is the slope of a position function. Why does that make sense? Because slope is y over x. So isn't slope a rate of change? Slope is a rate of change. And what is the name that most humans use for the rate of change of position over time?
Average rate of change.
No, most humans don't say that.
Speed?
Speed.
Power?
Speed.
Oh, speed.
Speed.
yeah.
I love it. And I'm just saying velocity because velocity is speed with direction. So I'm just using velocity because I'm a physics dude too. So I need to use velocity. Okay. So that's pretty straightforward. The slope is constant. This is a linear function. Therefore, the rate of change is constant and the velocity is the rate of change. So the velocity is constant. Okay. Oh my gosh. Okay. All right. So what if I have a position versus time that looks like this? Can somebody tell me just in words what this represents? What happened?
There's so much.
Yeah, go ahead.
I'm assuming they were getting further, and then somewhere in the middle they start coming back.
Exactly. They're like, all right, man, see you later. Oh shit, I forgot something. All right. Now, so that's just the fundamental thing about there's a one situation that would explain why I would have a shape like this, correct? And most of the time we think of this as like throwing a ball up in the air. So you can think of this as the distance away from you when you throw it up in the air. Well, at some point, you're not going to throw it hard enough to go into orbit. I would hazard a guess. It's going to eventually turn around and come back down. So let me ask you all the same questions. Is the velocity present on this picture somewhere?
Yes.
Where did you go? There you are. Anybody? It's the same answer. It's the same answer. The answer can't change. The
Yeah,
velocity.
velocity is present and it's, I guess, could you still call it the slope?
Yes. What is weird about the slope in this case?
Changes over time.
Because-
It changes every instant of time. So this is all algebra shit. Couldn't you figure out the slope of this? In fact, somebody help me out. Can you guys see this well enough? My little chicken scratch bullshit here. That's trying to be a 3. What is the slope of this line?
3/2. No, sorry, 2/3.
There it is. So it's change in y over change in x. And of course, 0, 0 is a point, so that makes it easy, yes? Is everybody with me? So that is algebra. Do you agree with me that every point still has a slope? Every point still has a velocity, yes? And we know that the velocity is the slope. So there should be a way. I can't, if I say, what's the velocity of this person? You can give me one answer, 2 meters per 3 seconds. Or you can say 0.67 meters per second. Is that cool? You can give me one answer, you're done. If I say, what's the velocity of this person? You would say, at what time? If I ask you, what's the velocity of this person? You can't give me one answer. You have to say, I don't know enough. At what time? For example, what's the velocity at this time?
0.
0, because that's where they go, oh shit, don't they stop for a second?
Yeah.
Turn around and start coming back at me? So like when I throw something in the air, doesn't it stop at the top? It's not going up or down. So its velocity is 0. I like it. I like it. So here it would be 0 because if I drew a line, now think about this. If this is something, all right, what's a good way to explain this, Jeff? Here we go. Are you the only thing I have close? Yes. Are you? I think you are. It'd be great if I could plan ahead. That's too bad for everybody. So, all right, I got this thing. I'm gonna twirl this thing around. I'm gonna try to. Let's see if this will work. There we go. Oh, geez, let's not hit myself in the face. You can't really see it. I'm spinning it too fast. But I got this thing, and I'm spinning it. Whee! Okay, right? What if the very end of it became disconnected? Right? If it became disconnected, how would its motion change? So right now it's moving in a circle. If it became disconnected, how would it start to move then?
Should move faster.
It won't move faster. It'll start slowing down because it's no longer attached to that which was making it move.
Wouldn't it like fly through the air or something like that?
Fly off in what kind of trajectory?
It's angular
No,
because
it
like
would become linear. It would
Oh.
fly off in a straight line. What's the only reason that it is turning as it moves? What's the only reason it's turning? Does everybody understand what I mean?
Gravity?
Not gravity. Because of this, the wire isn't since it's attached to the wire, it's got to stay with the wire. All right, I'm sorry. I'm not going to suddenly make this physics class, and I apologize, but I really want this to make all the sense in the world. Do you guys know those weapons that you would swing around then release? Yes.
Right.
You don't want that to go off in a circle. You want that to go straight at whatever the hell you're throwing it at. Yes. So the minute you let go of it, it's going to continue with the velocity it had when you let go of it. Okay. Let me reconnect this. Sorry. All right. Don't worry. I'm not going to make this a physics class. Don't worry. So the velocity at this point would be represented by a line that it would continue on. So at this point, do you guys agree with me? Let me see. So here it is moving. It's definitely zero here, yes? It's definitely zero velocity here. What do you think is true about the velocity on this side?
Negative.
Yeah, good. So it's positive velocity here. Then he starts to wonder, he's like, did I forget something? And he starts to slow down and goes, yeah, I did, shit. So he turns around and then he starts coming back at us faster. And we're like, whoa, stop. Okay, maybe. I really want this idea to make intuitive sense. So we've all seen movies where somebody swings something and they throw it, the little stick, on the rock on the end of a rope or something. So I like that idea of if it suddenly stopped following this, it would just go off in the velocity it last had. And it wouldn't continue forever in this direction, but locally, right here, that is its slope. Right here, this is its slope, 0, right? This line has the same slope. Right here, this line represents the slope at that point. Okay. So this question is easy because the slope is the same everywhere, right? And we have a process to figure out the slope everywhere. This slope is much more difficult because it's constantly changing. Now, the really, really beautiful thing is I can still use the idea of slope from algebra. I just have to add one thing on top of it. So is everybody kind of with me what's happening right now? I want to know, I want to have a way to figure out what the slope is at any time. Because here I can do it. At any time, the slope is this. There is definitely a speed this person's moving along at all these different points. There should be a way to figure it out. Okay. So I'm going to redo this picture because it's so beautiful. Hi. Okay. So let's do here because I got more room. Yeah, sure. Okay. So let's say I want to know the slope at this point, and let's call it A. And let's call this f of x, or f of t, I guess. Well, this is getting interesting, but it's not too bad. So can somebody tell me what this is? Let me write this bigger. The position is a function of time. So can somebody tell me what this is? What if I had y equals x squared, and I said, what is this? What is this? What would you do? What is this?
plug in the 2 in the
Plug in 2.
equation.
I like it. So at A, what is this plug in an a, it's f of a. Like it. Are you guys with me? Or is anybody completely lost? You have to let me know the minute I lose you. I want you to really understand what it is we want to happen. We want to know, because there is definitely a velocity at each of these points, correct? There has to be. There's a velocity there. There must be a way for us to figure out what the hell it is. Our cars are able to do it. Isn't our car telling us what our speed is at every moment? We're better than cars, right? They don't have a brain, well, I mean, sort of, but not really. Okay. What sucks about this? Well, how did we figure out the slope earlier? I can't remember what this was. Shit, I think it was 3 and 2, right? Yeah. How did we figure this out? What did you actually use? It was a little easier because of 0, 0, but how do you figure out the slope for a line? Why can I do it like this? What's the slope how would I figure this out?
Over 3. So rise over run.
Rise over run. So it would be 2 minus 0 over 3 minus 0, right? y2 minus y1 over x2 minus x1, correct? You guys with me? A little bit? Okay. So in order to figure out the slope of a line, how many points do you need?
Are we using triangles?
Not really, no.
2.
You need 2 points, correct? To figure out the slope of a line, you must have 2 points. Why does this suck then? I'm trying to figure out the slope of the line that would capture this guy's movement here, right? Why does this, what's the immediate problem? I've only got
Only 1 point.
1 point. Do you know any other points on this line? No, I don't. I have no idea. I don't know. I just know that the point a, f of a is on that line, correct? That's all we know. And that's not enough for our slope formula, right? Damn it. So what do we do? What do we do? Well, we're going to bring in the idea that we were using earlier. Wouldn't you agree with me that this is a problem point in a sense? It doesn't by itself give me enough information to figure out what's going on. So what do we do then? What we do, let me draw this again one more time. A little bit bigger. What we do is we pick a point. Oh, Jeff, that's the dead one. Yeah. All right, we pick a point. Wasn't that dead? Right there. And we find the slope of this line. We find the slope of the line going through those 2 points. Is that the answer that we want? The slope of the line through those two. What does h mean, by the way? Do you guys, a plus h here? Let me write that a little bit better. I really want you to understand what's happening. I can't find the slope with just 1 point. That's an absolute undeniable fact. So what I do is I go a little bit away. So this is just h away from a, just a little bit away from a. And then now I've got 2 points, don't I? But what did I lose? I got 2 points now, but is it going to be the right line? No. Do you guys see that? I really want you guys, because the line I want should be like this. Since I'm using that point that's further down, this line I'm going to get is the slope isn't going to be quite right. So what makes it better then? If I do what? What would I do to make it better? My approximation, I want to make it better. What would I do? Let's do this. Let's be more specific. Okay. Here, let me do a couple things. I'm going to give us an easier function to look at, okay? And then we're going to use some very specific stuff. Okay. So let's use the function x squared. What time do I have? Okay, got a little bit of time. And I want to know, and let's be a little bit specific here. Okay. Model good behaviors here. Okay. Let's say that we want to know the slope at, don't do this to yourself, Jeff. Is this the good one? Yes. We want to know the slope here at 1. We want to know slope of f of x at x equals 1. Okay. You guys with me? At 0, what's the slope?
0.
0, definitely flattens out, right? That's like at the top of the roller coaster. You're not going up, you're not going down, you're flat. And of course, back here it's negative, out here it's positive. So the slope here, as I move on, gets larger. It's 0 here, it gets larger. So I want to know what that slope is right there, right? If the roller coaster came off the tracks, how would it fly, right? Oh, shit. Okay. So, first approximation. Let's use something, a really shitty approximation. Let's use this point as a plus h. So this will be our a. So then, am I getting the right answer? No, my answer, is it going to be too big or too small, the slope here? If I use this other point, is that slope too big or too small?
Too big.
Too big. Everybody agree? Because it goes up a little bit more than it should. But it's kind of close, yes? Okay, so let's figure out. Can you guys figure out for me, what is the slope? Let me see, what's a good way I can say this? Yeah, let me say it like this. Average velocity on 1, 2. Okay, that sounds a little weird, because that's what you're going to see in the book. But all this is asking you for is, what's the slope between 1 and 2? What's that slope? So what points do you have to use?
1/1 and 4/2.
I got 1, 1. Careful.
4, 2. Or 2, 4. Yeah, my bad.
Just take a second. What's the slope then?
3?
Yeah, it'd be 4 minus 1 over 2 minus 1. 3. I like it. Now I can ask this question. How would we improve our approximation? How do we improve that? Does everybody agree with me that that's approximation and it's not great?
Plug in the 3 into the original equation, no?
Say again, sorry.
Plug in the 3 into the equation.
Plug a 3 into the equation.
So wait, so you plug in the 3 to the f of x equals x squared?
Plug in a 3 for x?
No.
No, because this doesn't say x is 3. This says the slope is 3. Now, can anybody tell me why this is a bad point to pick in the first place?
It's a bit far from the point.
It's a bit far. Sorry, okay. It's a bit far away, right? So how do I make a better approximation? Instead of using 2,
We can use 1.5 or anything smaller.
yeah, I would use 1.5 or something. So right here, when I'm at 2, h is 1. I really want you guys to get the parts of this. 1 is the one I'm interested in, yes? 1 is the point at which I want to know the slope. We said, let me use the input of 2 to get another point because I need 2 points for a freaking slope. In which case, how far away am I from what I was interested in? I'm 1 away. So what h means is how far you went away. So in general, how do I make my approximation better and better and better? I let h go to what? You can do it.
0.
Go to 1.
Yes, I let h go to 0? Why can't I let h equal 0? How many points?
Because then you don't have any points.
Then you only have 1 point.
Yeah.
So what idea that we just talked about allows us to get closer to something without actually using that? Is the limit, of course, right? You're all like, yeah, Jeff, we just talked about. Okay. Okay. So this is a very concrete problem. Later, we're going to do the more conceptual problems. We have to do more, less computational work. But the computational problem, let's continue with this. So now to make my approximation better, let's use 1.5. So now what are my points? My second approximation. What are my 2 points? I always have 1, 1, yes? Because that's where I'm curious about. And what's the other point now?
1.5 comma 2.25.
Kick ass. And where did that come from, of course? You just plug 1.5 in. I like it. So listen to me. This is not difficult. Every step is something you've done before. You've just never done all of this for one problem. Do you understand what I'm saying? So higher and higher mathematics, one thing it does is it takes stuff you've done before and puts it in ways that you haven't really done all of it together before. So you've done all of this shit before. You've done every single thing of this before. You've just never done it in this pattern, in this organization, for this reason. So now what's the slope? It'll be 2.25 minus 1 over 1.5 minus 1, which will be what, Jeff? 2.5. Yes? Is that right?
Yep.
I know math. Yay, it's my one skill. I got to show up. All right. So we were at 3, correct? Now we're at 2.5. How do I make it even better?
We can go down to 1.1.
Yeah, third approximation. This will be the last one we do. The last one of these we do. We got a little bit more we can do. So now my 2 points will be 1, 1, and what did we just say? 1.1 comma 1.21. Yes? Is everybody cool? Everybody understand where everything's coming from? You guys with me? Let me know if not. It's okay. Let me say this. If you have a question, at least 8 other people have that same question. You can be their hero by asking the question. Don't just sit there and go, nobody's asking. Everybody knows what they're doing. I'm not going to say anything. Do not let me bulldoze you, right? I have a tendency to get a little excited and go. Please ask anything. And you can send me a private message if you're shy and you don't want anybody to know you're having trouble. Shoot me a private message. I'll be the only one that sees it. Does that make sense? You guys with me? Okay. So now the slope is going to be 1.21 minus 1 over 1.1 minus 1. So you get 2.1, yes?
Yes.
So even by itself, can anybody give me a guess what the slope right at 1 is going to be? We had 3, and then 2.5, and then 2.1.
What's the 2?
2.
2, yeah. And it turns out it is 2. You might have to do a couple more just to be sure. But you can already see it sort of slowing down. 3, 2.5, 2.1. You do one more and you're going to get 2.0 something. And then you're like, okay, I think it's going to be 2. Okay, I like it. So let me formalize this process we just used. Okay? I'm going to formalize this process. Holy crap. I'm going to destroy all of my possessions. No, okay. So if I have a function, given a function, and I want to know the slope at a point A, f of A. Good Lord, Jeff. I write approximately in English. Slope is what? That's what we want to know at that point. That's what we want to know. What we do, Now here's what's interesting. I want you guys, now let's see if I can help get you to piece this together, and this might look familiar to some of you guys. The idea is to take something some distance above, I could go below also, it doesn't matter, some distance away from A. And the only reason we do that is because the only way to get the slope is to have 2 points. That's the only way we know to get slope. So somebody help me out. The slope is y2 minus y1 over x2 minus x1, yes? What 2 points do I have up here? I've got A, f of A. What's the other point that I have?
A plus H.
F of A plus H.
Yeah, A plus H is the input, and f of A plus H is the output. Right? So I have these 2 points that I'm going to use. So what does this look like now? What's y2? You can do it. Here's y. It's the y piece, right? The second point. So f of A plus H minus
F of A.
f of A over A
A
plus
plus
H.
H minus A.
And of course, the bottom becomes what happens at the bottom?
It becomes H.
Yes. Does that look familiar to anybody?
Looks like number 3. on the
Yes.
survey.
If you've done the very beginning of the first homework assignment, that is what they talk about. Yes. Okay. So this did not look familiar to you. That tells me you haven't started the homework yet. Shit. It's a bad place to be. Start the homework. I really want you to understand when you see this, you know it is saying this in a specific instance. That's all this is. This is still algebra right here. This is still algebra. It's not calculus yet. When does it become calculus? This becomes calculus when I make it hard. No, this becomes calculus when we bring in the idea of improving the approximation. And can somebody capture what we do to improve it? Don't I improve it by making this get closer and closer? Yes? And then what's happening to H to make that happen?
Getting smaller.
So the limit as H goes to 0. That is the formula to figure out the slope at a point. Like now, let's do some specific things that I want to point out some specific things because I've done basically the first 3 sections of chapter 2 just kind of like in different orders. I really want it to be clear to you what's expected in each section, and then we'll call it a day. Okay. So let me show you an example. Whoa. I got the book here somewhere. Hold on. I've got the book. Oh shit. Let me do this first. I forgot I had this. I'm drawing all this crap, and you poor people are having to deal with my pathetic drawing ability. And I have this beautiful thing. So can you guys see H here? Right?
Yeah.
So the idea is I want to know the slope here at this purple point. So what I can do is I can, holy crap, that goes fast. I can take this and I can come in. I thought I made you step by 0.05. I did. Good. Okay. Will you do it now? No, you won't. You little twerp. So what I can do is I can step in. So this is basically what we were just doing, right? It's just not being as smooth as I want it to be. Dadgummit. I thought I had this working earlier. So I can step in, and I just can't. At this point, do you see how it's telling me the slope is undefined, of course, because it's only 1 point. Can't do that. Okay. All right, sorry guys. So let me show you. Yes, I'm still here. All right, here we go. So this is that problem that we were talking about earlier, number 3. And anyway, all right. So let me go to part 2. How do I do that, Jeff? Oh my God. Sorry, I hate ebooks. Oh, I signed out. That's why it was freaky. How's everybody doing? You guys all right? Oh man, I signed out. That really sucks. Dooby dooby doo. You better freaking do it automatically. I don't know what my password is. Okay. Dooby dooby doo. What time we got? Okay, we're doing good. Okay, everybody. Oh no, come on with this. All right, hold on, guys. This will happen someday. Basically, section 2.1 is all about the concrete 2 points approach, right? So let me show you an example real quick. So you're not going to do anything with the limit yet in section 2 and section 2.1. So in section 2.1, you'll see a problem like this. And they'll say if P is this point, so that's the point you want to know the slope at. Find the slopes when the other point is 5,694. I really want you guys with me. Is everybody with me? That's exactly what we just did when we did the concrete numbers. So you would put, this would be y2 minus y1 over x2 minus x1, and you would get the slope, and then you would go to 10. So this 15 to 50 would be like 1 was. It's the one that's just staying the same, because that's the one we're interested in. Does everybody understand? There's no limit you have to do here. It's just plugging shit in and getting really close and really far away. Okay. And that's basically 2.1. That is basically 2.1. There's no limits yet. It's just finding slopes between points and letting the other point get close to the one you're interested in. So that is what section 2.1. They just ask you the same question in a lot of different ways. So you have to let me know if the words they're using are strange, right? All right. Section 2.2 gets into limits. So I kind of did this first, and then I went back to 2.1 because it just makes more sense to me to do that. So section 2.2 is about making tables like we did to investigate what's happening when you get really close to something. Okay, and this is where they introduced the notation. I love it. So section 2.2 is all about making tables to investigate limits of functions. Just like this. Right, so approaching one from the left and approaching one from the right. Oops. Do you see how they don't do it like I do it? You could do it either way, whatever makes more sense to you. And then section 2.3 is where we haven't really gotten to section 2.3 yet. Come on, continue moving forward. If I knew how to do this quicker. Okay, here we go. This is the next thing we're going to talk about, is just how do limits themselves work. Whenever you learn some new process, you want to know the algebra of that process. What's the limit of the sum of two functions? Well, it's the sum of the two limits. Okay, so we're going to do that next. So what homework should you be able to get into? Section 2.1, section 2.2, for sure. Right, definitely chapter 1 homework. That should be done soon. Oh, I'll be quiet with your error. Okay. All right, guys. I think that's enough stuff for today. What do you guys think? Is that enough? Hang out now if you have any questions right now for me. I put up in Canvas, last thing, I'm sorry, I put up in Canvas the Zoom link for my bonus office hours. They start at 11:30, right? So when we're back on campus, that'll be in the Math Study Center. For right now, it's a Zoom link. So if you go to the office hours on Canvas, let me show you that real quick here. Nothing is quick, Jeff. I know, nothing's quick anymore. Oh, it's right there too, is it? Oh, no. So if you go to my office hours, I've added in this piece. So Wednesdays at 11:30, I'll be at the Zoom link if you want to. If you don't want to, don't come. It's not necessary, right? Okay, cool. All right, guys. So I'll see you Friday. And if you have any questions right now, hang out afterwards and let me know. Otherwise, take care. Good job making it through that. It was a lot. You guys all right out there? Okay. Everybody good? Are you guys actually there? I'm going to head out. If you're there, take care.